some work that was published recently. I'll talk mainly about that, and then I'll talk briefly about some directions that we're working on recently. Okay. So the title of the work is Quantifying Uncertainty in Heritability Estimation Using Linear Mixed Models. So I guess like in this group, I don't need to talk a lot about heritability, but just to go briefly, so heritability is defined as the proportion of variance of a trait that is explained by a genetic component. And to put it into like a more specific model, let's say we have a phenotype Y, and it's assumed to follow this specific type of normal distribution when you have a mean, and then the covariance matrix, the noise, is composed of two matrices, K, which is the kinship matrix, and I, which is the identity matrix, which is an IID noise. And then we have two components, sigma G and sigma E, which are the relative weights of the different two sources of noise. So heritability is defined as, in this scenario, which is a narrow sense SNP-based heritability, is defined as the sigma G squared divided by the sum of the sigmas, which is, again, the portion of the variance of the trait explained by the genetic component. Okay. So this is the standard setting. So in this talk, I'll talk about three data sets. One is the NFBC data set. It has 2,500 people. GTEx, which is smaller, it has like 180, and Lurik, which has like 800. Okay. So before going into the details, let's just do like something very concrete. So let's say that we have a phenotype, and in this case, it's simulated from the NFBC dataset, and we're trying to estimate the heritability using REML. So the way it looks usually is that we run the GCTA program, and we get all these numbers here, and the numbers that we're interested in is this one, this row here, which means that the heritability we estimated is, let's say, 0.4 more or less, and then we have here the standard error, the holy standard error, and this is how we quantify the uncertainty in our estimate in general. So, So what do we do with this? So basically, the standard use of standard errors is to use them to construct confidence intervals, CIs, for the true value of heritability. So the way it's done is that we assume that the estimator distribution is normal with a variance that we know, and usually calculated from some Fisher information matrix or variance of it. And if we ran this program, GCTA or something else, and we got an estimate and also a standard error, then what we do is, if we want to construct a 95% interval, we take, let's say, more or less plus minus 2 standard errors above the estimate, and then we say that we think that our value is in this range, right? This is the standard thing that people are doing. But the thing to remember here is that the assumption of the normality is not trivial at all. And in fact, in order for it to hold, you have to have some assumptions like asymptotics and other things that do not necessarily hold. So in this specific case that we saw before, let's say that we got this 0.39 estimate, and if we take 2 standard errors in both sides, we get this interval, which actually looks kind of okay, and we are thinking that this is how the distribution looks like. But as anyone who's done heritability estimation in practice, often you get some very weird things. For example, especially if the sample size is small, but also in other situations. So one example is this. We have the GTEx dataset, and let's say we did a heritability estimate, and we got this heritability estimate of 0.089. And we got the standard error. But then the standard error is larger than the estimate. So what does that even mean? So that means that if we were to construct 2 standard errors from each side, it would be over the range of heritability, which doesn't make any sense, because heritability by definition is between 0 and 1. So this is very confusing, and we don't know what to do with this thing, and that's a problem. The problem is that we assumed normality, which obviously doesn't hold in this case. So here's another thing that happens a lot. We get a 0 estimate, like a completely 0 estimate, and then of course we have the same problem of what do we do with the other side here, and that's also very confusing, especially for a lot of people who run this and get a 0 and they think something went wrong with the analysis, because it's everything is like continuous. Maybe you hope to get some 0.03 or something, and then you get this exactly 0. So everyone is very confused and sad. Okay, so so we were saying that the problem might be because the normal distribution assumption is wrong. So one way to check this is to actually see how the estimated distribution looks like under the null model, the true model that we're assuming. So let's say we have we assume a certain heritability value of 0.1. Then we draw 10,000 phenotypes from it, and then estimate the heritability using our method of REML again and again. And then we just see what we get. So we get this histogram here. So on the x-axis, we see the estimate, and on the y-axis is the probability of getting this estimate. So we are binning this probability, this range, because it's continuous. So we have like one bin at 0, one bin at 1, because it's the boundaries. So that's important. And then in the middle, we divide it to 100 chunks, and we get this thing, which obviously doesn't look normal. We have this peak here, like on the left, but we see that the probability of getting a 0 estimate is very high. So this maybe explains why we get a lot of 0 estimates. And we also see that the normal distribution is not very good. And we can do that also for a 0.2 estimate, and we get something which looks more normal, but still we get a peak at 0, and maybe at 0.3 it's fine, so maybe that's okay. But then we can do it for the other data sets, for example, for GTEx, and this is how it looks. So this is very far from being normal. We can see that we get high estimates for 0, high estimates for 1, and if the true value would be higher, it will be even higher. So, and the same thing goes for the third data set of Lurik. So yeah, so we see that the assumption of normality is very, very wrong. So basically, constructing CIs based on that is obviously going to give us like bad results. So the next thing we want to do is to measure how good the CIs are, for the CIs constructed by the standard errors. So the natural way to do it is, let's say we have the true value, the true heritability value, and then we can, again, draw phenotypes from this heritability value, and then we estimate the heritability for each one, and then we have a standard error, for example, by running GCTA, and then we construct the CI as we would, and then we check how many times the true value, which we know was in this interval. And if the interval is well calibrated, it's accurate, then it should be exactly 95%, if this was a 95% interval. Yes, exactly. So we can do that for the method of CIs with standard errors, and we can see, for example, this scenario here, like in the GTEx data. So what we see here on the x-axis is the true value of h squared, the heritability value, and then on the y-axis we see the actual coverage of the CI as we just measured it, as I just explained. And if the CI was accurate, this should have been on the straight line over there. That's the 95% line. And we can see it's well above it sometimes and below it, so it's very inaccurate. And for Lurik, it's above it for some reason. I'm not sure why. And this is the same thing for 90% CIs. Again, it should have been on the 90% line, but it's not. Okay, so now we're convinced that the CI construction method of using the normality assumption is wrong in many cases. Oh, here's a couple of more slides. I forgot they were here. Okay. Okay, so motivated by this inaccuracies, we developed this method, ALBI, which does basically two things. The first one is, suppose we had the empirical distributions of the estimator at each true value for heritability. We define a way to create accurate CIs, which have the exact coverage probability. And the second thing is how to actually calculate these distribution of the estimators by using a parametric bootstrap, but we're doing it using some tricks to make it much faster. So this becomes tractable and feasible and doesn't take forever. Okay, so the advantages of this method are that it constructs accurate CIs, and it doesn't assume all the normality assumptions that we had or any asymptotics, and also that it's very fast relative to doing like a full bootstrap that people are sometimes doing. Okay, so I'll first talk about how to construct CIs very briefly. So the way to do it is to use a method from statistics called test inversion. the way it works is that, let's say that we have the estimated distribution given a true value for all the values of all the true values that we have. So first we define an acceptance region, which is a subset of the estimated values, which is exactly a region that occurs in the probability of 1 minus alpha, which is in this case 25 and 95%. And this is like, if we had a test, this would be the values that we would not reject the hypothesis that the true value is the h square, the blue one, blue a square. So if we had these regions for all the true values, then to construct the CIs, we invert this, which means that we select. So if we had this value for the estimate, the CI would be all the values of heritability for which the estimated value is in the acceptance region. And then this becomes exactly accurate. I'll skip this. And the coverage is exactly right. So here's like a nice drawing of how this works. So on the left side, we see, like before, the estimated distribution. So let's say we select the region of somewhere between 0 and 0.3. This is the region. And here we draw it here, this region for the 0.1. This is true value of estimate. And let's say for the true value of 0.2, we select 0 to 0.4. And for 0.3, we select something else. And now 0 is no longer in this. And then we continue all the way. And then in the end, we get this kind of like selection of regions. And well, in reality, it wouldn't be like all linear and nice. It would be like nasty, but this is a drawing. And then once we've done that, we use this to construct the CIs by inverting this, which means that if we had like, if we got an estimated value of 0.4, then the CI would be all the values that are here, like all the values in which the estimator is in the region. Okay, and this is how it's done. Let's skip this part. Okay, so so here's what happens when we run this method on the GTX data. So instead of having all these skewed lines after building the accurate CIs, we get exactly the lines that we need. Like everything is exactly on the right number of accuracy that is. Okay, and the same for Lurik. And about the fast parametric bootstrap, I think that I will skip it. But basically, the idea is that we, instead of estimating doing a full bootstrap, we just look at the derivative of the likelihood to make a fast decision. I'll skip this. If someone wants to hear about it, they're welcome to come and talk to me later. Okay. So here's how the speedup is. So if we were to have a like parametric bootstrap, which means that we draw a phenotype and then estimate it with some method, for example, GCDA or PyLMM from Zar's lab, then it would take, let's say, look at the last line. It would take the first line. It was 8 hours with GCDA and 1 hour if you do it with PyLMM, which is faster. But with Albi, it would take 27 seconds. So this becomes very, very tractable. And we can do it only once. Okay, so to sum up this part, the current methods for constructing CIs are inaccurate, and like having inaccurate CIs is bad because it can lead us to having wrong decisions about the heritability of a trait, and Albi is a method that solves all these problems nicely. Okay, and this is work that was done with several people. Eran is my advisor, and Saron here, and also Zar, and Shachar Kaufman, which is not here. Okay. So I'll talk very briefly about things that I'm interested in now. So one thing that I'm thinking about is permutation testing for heritability. So as a follow-up to the previous part of the talk, so often we want to ask if a heritability of phenotype is non-zero to do statistical testing. And when we have parametric methods, for example, the LMM, this is very nice because they can be very powerful and can say meaningful things, but then we have to assume the model. And we know, especially after last week, that in many, many cases, the assumption of the model is wrong for various reasons. Maybe it's case control, ascertained, so maybe the additive model is wrong, et cetera, et cetera. So one alternative to that is doing permutation testing, which is non-parametric testing, which basically means that if we have some way to measure the correspondence of phenotype and genotype, for example, heritability, then maybe we ask ourselves, if we were to permute all the individuals to switch their names randomly and then calculate the heritability again, would we get something which is larger than the heritability estimate that we got already? And if we don't, for a lot of permutations, then maybe we believe that the heritability is significant. Okay, so this is what it means here. We permute the phenotype again and again, and then we calculate the heritability, and then we ask if it's larger than the one we got, and the p-value is this guy here. And yeah. So we're thinking about using ideas from Albi and other methods to do it much faster. Currently, we're having about 2 orders of magnitude improvement, so this makes it much faster. And here's a bit of motivation. So we tried running this heritability testing on all the methylation sites in the dataset we have, the core dataset. So each point here is a methylation site. So on the x-axis is the log p-value that you get from running 10,000 permutations. And on the y-axis is the p-value that you get from GCTA, which are making some kind of a asymptotic assumption. And you can see, like in general, that GCTA as p-values are much smaller. So they may result in false positives and actually more extreme results. So people know, have like methods to calculate better p-values, but this is a very preliminary analysis. And okay, so like other stuff that we're working on very briefly is taking Elior's method that he talked about 2 talks ago and building and analyzing the theoretical basis of that to see that when it works and how does it work better than other methods. And also thinking about analyzing confounders that are in 2 data sets. For example, maybe population structure in genotypes and methylation data, and see if we can do something smart about that. And yeah, that's it.